Let's get started. So we're going to do something a little different today. Rather than me talk all lecture, you're going to be doing some work. I did post the notebook that I used last class, and I added some information to it. Did you get my email I sent out last night? What's that? No. Yes, I was going to say very good tunnel vision. Yes. Um, so when you compute these models, there are a number of different things. Usually, people then various metrics you can look at. One is what they call the confusion matrix. I don't know why it's called the confusion matrix. So here it is, the model we looked at last time, and this is the data looking at admitting or not admitting students to graduate school based upon GRE scores, GPA scores, and the rank of the schools. And they typically, you look at 4 different categories. One is, well, you denied them. How many people did the model predict that they would deny in your test set? And how many that people were actually denied, actually the model said they'd admit. And then you do the same thing with, right, the yeses. How many did the model predict they deny, and how many did you predict they would admit, right? And that gives us some feel for how well it's doing in the sense of it, how many did it get right, and how many did it get wrong in the various categories. Doing the actual raw numbers makes it a little harder to see what's going on, because is 75 good? Is 12 good? Well, it depends upon how many data points you've got, right? Where am I? Come on. So there's a number of other measures people will do. One is accuracy, just how often is the model correct, right? And that is the total the true positives, true negatives, divided by the total number of elements. In this case, the model it got the predictions right about 3/4 of the time. How often is the model wrong? Well, if you know how often it's right, you know how often it's wrong. And then there's the true positive rate, or we call it sensitivity, and that is when the answer is yes, or in this case admit, how often does a model predict yes? Right. So in this case, it's not very good, right? 39% of the time when a student is actually admitted, the model predicted they would be admitted. False positive rate, when the answer is actually no, how often does it predict yes? It's much better at that, right? And then we go on to specificity. When the answer is actually no, in this case, deny, how often does the model predict deny, right? Right, so there's various measures like this. And depending upon what you're trying to do, you may favor false positives over false negatives, right? So if we're doing a medical test for some fatal disease, we may prefer to have false positives over false negatives. Because if you have false negative means you say the person is not sick, but they actually are, and then later they can die, right? So you may prefer a test where we want more false positives and fewer false negatives, and then the positives may go on to a more sensitive test. Okay, any questions? No questions. Okay, so like I said last time, what I want to do today is, given all these computers sitting around, each table, select one of decision trees or random forest, and then compute. So, create a model based on this data set of the iris. Get the model running, right? Divide the data into a training set and a test set, and then compute the accuracy, specificity, and precision. And we do it on the iris data set. And where to get the iris data set? Correct. Questions? Everyone understand what they're going to do?